So yeah, so what have we done? I think the principle of mathematical induction is something we can do a quiz on. And then what else? We have the theorem 1.7, every integer is a product of primes. So that's a theorem we could put on a quiz. And then theorem 1.8, the fundamental theorem. The fundamental theorem is, yeah, I mean, it's kind of like that has the uniqueness bit in it, right? The fundamental theorem, so theorem 1.8. So, and then do we have definitions? We have the definition of prime. So we could do definition of prime. Okay, so here, let's do these. Let's do for quiz for Wednesday. We'll do the definition of prime. Right, and so the definition of prime is that it has the only divisors are plus or minus 1 and plus or minus p, right? So p is prime if it has those divisors, okay? And then we'll do like theorem 1.7, which is the product of primes. And then we'll do the induction, the principle of induction. The principle of mathematical induction. So those are your memory things for next Wednesday. Good? Okay. So yeah, let's get started. So maybe we should write down the principle of mathematical induction now so that we have it. Okay. Okay, so the principle of mathematical induction says okay, it says assume that for each non-negative integer n, we have two things. So the first thing is that p of 0, oh wait, no, sorry. We have a state, we need to say a statement pn is given. So if these two conditions are held, p of 0 is true. Or like I said, this says p of 0 is true. You could do p of 1 or p of the smallest one, right? So whichever is the smallest in that it holds for. So a lot of times that's the p0. We could also do like p1, right? So depending on what the statement is. So the second condition is that whenever pk is true, pk plus 1 is also true. And then we can say then p of n is true for all non-negative integers n. Good. Okay, let's do an example. And I'm gonna have y'all work on this in groups. I think you're pretty, I mean, did you just follow the statement to write the proof? That's basically that. So we've got proof that 5 is a factor. Okay, here's a of 2 to the 4n minus 2 plus 1 for every
positive integer. So we're gonna do this prove by induction on n. Well, n's the only thing we could do induction on, it's our only variable, but so that's what we've got.
All right, so go ahead and get started on that. We may have to work together a little bit on the algebra on this one because it gets a little hairy in the middle, but I think y'all can get started on it. So work together on that. Jose, we're gonna have a quiz on Wednesday, and it's gonna be the principle of mathematical induction, the definition of prime, which is P is prime if and only if plus or minus 1 and plus or minus P are the only divisors. And then theorem 1.7,
Okay.
which is the product of primes. Yes,
For those, are you wanting us to go like proof for them or just what they are?
just the theorems, yeah, just the statements. Yeah, did you all hear that? For the quiz, just the statements of the theorems, not the proofs. Okay. But we can prove theorem 1.7 by induction. Actually, we could do that today if you want to. It's pretty easy.
So from 0 to 4.
Yeah, I was about to say. You said the definition of primes, theorem 1.7.
And the principle of mathematical induction, which is this.
5 divided 2 4. So we're dealing with that, right? So assume 5 divided 2 to the power 4. Yeah. And then we'll just start with 4, like floating. And so like exponential, so I take the 2 to 4. All the- Basically, I just said hold it to this mark. And then 2 to 4 plus 2. This thing is the thing we know from the assumption. Well, no, it's 1 for this plus 1.
I was trying to get it to switch to the side.
Yeah, the plus 1's outside.
But you can still have the negative one.
True.
No, you're right.
Yeah, the issue is it makes 1 positive.
Yeah.
Wait, does this work for n equals 0?
Says positive and
Okay, so so our base case then is n equal 1, right? Yeah, okay, y'all caught that already. Okay, good.
Oh, it says- so it would be part of this.
All right, so what's our base case?
N equals 1.
Sorry, yeah.
For that, we've got
So,
2.
it's easier to show that there's. On the right, here's the last one. Yeah, so the last digit is always 1.5, so if you can show the last digit, this is always 4.
Sounds good. What do we assume?
That 5 divided by that.
Positive integer one. Okay, so then what do I need to, oh, I didn't do that, +1. Okay, then what are we trying, where are we trying to go here? We want to get that 5 divides 2 to the 4 n plus 1 minus 2 plus 1, right? That's the reason. Okay, any thoughts? So where do we start? Yeah, Colin?
I wanted to say, this is not done proving, I just mean this is something to try to prove to do it. I think what happens is this is always odd. So if it's divisible by 5, the last digit is a 5, so possibly would it be easier to show that you do division algorithm and if you divide it by 10, the remainder is always 4. And then you plus 1 is 5.
If you divide this by 10, not without the
yeah.
+1,
Yeah, you get the remainder 4, so then you add the 1, the remainder would be 5, and then you
that, let's see, so that's a different take than I was doing, so I have to slow down and wrap my mind around that, so maybe, I mean, that might work, I think that's a reasonable idea. Were you gonna still do that by induction? I think it would be hard to do it by induction with that, I mean, I'm not sure, I'd have to think about it. Because like if you had that 2 to the 4n minus 2 is divisible or has a remainder of 4 upon division by 10, then what about 2 to the 4n plus 1 minus 2? So you have to like use that fact that 2 to the 4n minus 2 leaves remainder 4 upon division by 10, right? To show that it's true for the n plus 1 case, you know what I'm saying? So maybe it works, I don't know. Actually. Let's do a more algebraic thing and then we can explore that. Does that sound good? Okay. So what's another thing we could do? Somehow I want to use this fact, right? But I want to start with this guy, 2 to the 4n plus 1 minus 2 plus 1, right? And then what can we do with that? Did y'all get something? Did you get something from there? Did you get stuck? Y'all were talking so well. Okay, so do you need a minute to fiddle with that?
We like factored out, like
Mm-hmm.
distributed, and then factored out as 2 to the 4.
Okay, so we got 2 to the 4n plus 4 minus 2, right?
Mhm.
Is that what you mean? Plus 1?
And then we got stuck because it was, what did it end up being?
It was 2 to the 4 n minus 2, and then in parentheses, you multiply that by 2 to the 4, and then outside of that, you add 1.
Oh, so you took out a 2 to the 4n,
Just 4.
2 to the 4, okay. And what's left? Well, oh yeah, so that we're basically taking that guy out, right, of the exponent. So we'll have 2 to the 4n minus 2, and then all of that plus 1.
So the plus 1. Because if it divides one of the fact, like one of the products, it does. It divides it, but the plus 1 was tripping us up.
The plus 1 is tripping you up, yeah, yes, so that's true. So it'd be great, it'd be awesome if I could factor that 2 to the 4th out of the whole thing, you know, and then I'd have, I'd have something that I could say. So this is kind of one of those situations. Well, does anyone have an idea? This is kind of one of those situations. Okay, so in mathematics, a lot of times what we do is we multiply by 1 in a special way or add 0 in a special way. Okay. So doing those things can sometimes get us some footing. So any thoughts on how we could add 1 in a special way or add 0 in a special way? Yeah, Colin?
We're not allowed to do like 2 to the power of minus 4 yet, are we?
No. I mean, maybe. What was your thought?
But you mentioned multiply by 1. If you turn the 1 into 2 to the 4 times 2 to the minus 4, then you have a 2 to the 4 in both parts, and it could factor out, and that maybe that goes.
Okay, so changing that 1 into 2 to the 4th times 2 to the minus 4th.
Yeah, but then that's
But then when you factor that out, we still don't have exactly what we want. Yeah,
Oh.
so because we'll have a 2 to the minus 4th left over in there. Okay, so here's the idea. You could take 2 to the 4th, 2 to the 4n minus 2 plus 2 to the 4th. Oh wait, we need it to be, yeah, minus 2 to the 4th plus 1. So you add and subtract the 2 to the 4th. And then now what? Now what can we do? Well, I can pull the 2 to the 4th out of those first 2 terms, right? We'll have 2 to the 4th times plus 1. And then what's this stuff? So that's minus 2 to the 4th is 16. So that's 2 to the 4th times 2 to the 4n minus 2 plus 1 minus 15. Good. There you go. Which is divisible by 5. Yeah, exactly. So how do I rewrite this guy? If I know that 5 divides that, what's the definition of that? How do I rewrite that in a useful way? What does this mean?
Whatever case.
Yeah, so 2 to the 4n minus 2. So I can say since, and maybe I should have said that, could have said this at the beginning, but since 5 divides this, we can say that 2 to the 4n minus 2 plus 1 is equal to 5k, where k is in z. Okay. Right? Okay. So now I can replace that bit with the 5k. Yeah, I kind of interrupted my flow here. Maybe I should have said that like right after my assumption, and that might have been a better flow, but anyway, whatever. We're doing this in real time here. So I get 2 to the 4th times, and I can replace that with 5k minus 15. So I can pull a 5 out of that. So I pull a 5 out, I get 2 to the 4th. Wait, what do I get? Times k minus 3, right? Which is divisible by 4. So 5 divides that, I think I started with 2 to the 4 and plus 9. Okay. So this little trick here of adding 0 in a creative way, or sometimes you multiply by 1 in a creative way. Like, remember back in when we were doing, when you had to like multiply by the conjugate on the top and bottom and things like that. So this is kind of one of those types of strategies that you can use from time to time to get some footing. So especially when you're trying to divide, if you're trying to, we got to here and we're like, man, if I could pull that 2 to the 4th out somehow, right, I'd be in business. And so you start thinking about, okay, well, maybe I could write that 1 as 2 to the 4th times 2 to the negative 4th. Oh, that doesn't work. Well, maybe I could add 0 somehow, right? So you've got to kind of have these little tools in your tool belt to grab from when you need them. Okay, questions on this? Okay, there's one really similar to this in your homework. So I wanted to show you this bit before you had to tackle it in your homework. But are you clear how to set up these proofs? I mean, the base case definitely, is usually pretty straightforward. And then you write out your assumption, and then you start with the n plus first case, right? You start with p n plus 1, and you try to get it to where you can use this assumption somewhere in your chain of equalities there. Okay, so that's where we're trying to. That's kind of the setup, and they're all pretty much the same structure. You just may have to have some algebraic tool or whatever in the middle to get it, make it work. Okay, so Colin, your idea was to say something about how 2 to the 4n minus 2 is divisible by 4. So let's try that. So do you understand what Colin's idea was? So we could say that, or when we divide by 10, so we want it, so the idea is that saying, okay, so the case that n equals 1, I'll have 2 to the 4n minus 2, which is equal to 4. And so, so 4 is equal to 10 times 0 plus 4. So by the division algorithm, that's my remainder. So 4 leaves remainder 1 upon division by 10. Okay. Remainder 4 upon division by 10. There we go. I got some funny looks there for a second. Okay, so we can assume that, okay, so let's assume that 2 to the 4n minus 2 is equal to 10q plus 4. Maybe for some, maybe we'll call it q1 because that's like a specific q. Okay. Okay. So then, what can we say? Okay. Then 2 to the 4 n plus 1 minus 2 plus, is equal to what? Okay, so now I can pull out the, okay, how does this work? How's this gonna work? Okay, so same thing, I get 2 to the 4n plus 4 minus 2. So I can pull out the 2 to the 4. Right? Okay, so, okay. All right, this may go somewhere. Let's see. Okay, so I'll have 2 to the 4th, and then I can replace that with this, right? So I'll have 10q1 plus 4. Okay, now unfortunately this is 16, so maybe, so let's see if we can, okay. So we'll have 10q1 times 2 to the 4th plus 6, so 2 to the 4th plus 4. Okay, so this quotient is fine, but my remainder is too big, right? So can I pull a 10 out of that? Well, let's see here. Okay, so I have 10 times 2 to the 4th. What's that? So that's 16 times 10, so 160. No, I want to leave it as 16. Oh, gosh, dang it. Okay, so I want to leave it this way. I want to say 10. I want to do 10 times the quotient, right? Yeah, okay, so 10 Q1, 2 to the 4, plus, and then can I, so this makes 16, that makes it, oh, shoot. That makes it 16 plus 4, that makes 20. No? Oh, that's times, it's times,
Right.
it's times, it's times. Okay, so sorry, I was being dumb. Okay, so 16 times 4, what's that? I have no idea. Okay, 64. Oh, look here, yeah, 64. Oh, that's good. Okay, so that's 64. So that is 60 plus 4, right? So I think your idea is gonna work. Okay, so that equals 10 Q1 times 2 to the 4th plus 60 plus 4. So I can pull a 10 out of all that. So I'll have Q1, 2 to the 4th plus 6 plus 4, right? So then that's my remainder is the right size. So I get that this guy leaves remainder 4 upon division by 10, right? So 2 to the 4 n plus 1 minus 2 plus 1 equals 10 times that stuff plus 5, right? Which is divisible by 5. Yeah. So that works. Very nice. And the nice thing about that idea is that it gave you some traction because you could pull out that 2 to the 4th. You didn't have that pesky plus 1 to deal with. So that made it kind of nice. So yeah, so I'm not sure. I didn't work the other problem out. Well, I did work it. Did I work that problem out in your homework? I don't remember. I try to work all the homework problems before I give them to y'all because sometimes you can pick a problem you think is going to be nice and then it ends up being terrible. So I don't remember. This strategy might work on the homework problem. I didn't try it that way, so I'm not sure. So okay, so there's that. Do you want to prove theorem 1.7 by induction real quick, and then we can do the division algorithm by induction? Let's do the theorem 1.7. Theorem 1.7 is that every integer can be written as a product of primes. So let's say integer in let's see. Okay, so that is every integer. So that includes negatives, right? So we're gonna have to adjust a little bit to use induction because induction has to be on positive numbers, right? So let's say proof. So we'll put a little statement at the beginning and say like, okay, if I can find if n is less than 0, right? Then I can find if I can find a prime factorization for the positive version of it, right? Then I can find a one for the negative version. So that's kind of the idea. So how are we going to say that in words? Okay. So assume n is greater than n is let's just assume it's a natural number. If we have a prime factorization for n, we can make a prime factorization. We can find a prime factorization for negative n by just making one of the primes negative. So therefore, we can just show it for the positive ends, right? Does that sound good? Okay, so proof by induction on n. So our base case is n equal 1. So is n equal 1 a product of, well, okay, let's start with n equal 2, because 1's not prime. Yeah.
I was reading about this one in the textbook, so I don't know if we're doing it in this class, but I was reading somewhere else that there's this empty product convention, that the product of no primes, it's like 2 to the power 0 or
Oh,
3 to the power 0.
I mean, okay, so in mathematics, you define things in a way that's convenient for a purpose, right? And so, so it may be that in some instances, it's convenient to define it that way. I'm not sure what the utility of that is off the top of my head.
Yeah, I
So,
didn't know if it might not be useful in this like the way the textbook's doing it, so I
Right.
don't know, maybe it doesn't matter.
yeah, I don't know. So let's assume that n is not 1 because, well, because I think that it says every integer except, right? 0 and plus or minus 1 can be written as a prime times, and that's in there. So we're gonna assume n is not 1. So our base case is n equal 2, but 2 is prime. We're done. Right. Okay, our induction step, we're gonna assume n can be written as a product of primes. Oh, no, wait, is it the other way around? Hold up, do we do this by contradiction? Okay, we'll do it by strong induction, actually. So we're gonna assume that K is a product of primes for K less than or equal to N. Okay, so this is actually strong induction. So strong induction is similar to the induction, but this says whenever P, like whenever it's true for all of the ones before, then it's true for that one, right? So this regular mathematical induction is just says, if you know the K one is true, then the next one is true. But strong induction says, if you know that all of the ones before are true, then this one's true. Okay, so we're actually using strong induction here. But both of those are defined in appendix C. So, or appendix, what appendix are we in? C? I don't remember. D, maybe? I'm not sure. Okay, so assume that K is a product of primes for, yeah, for all K less than or equal to N. And then we'll assume by way of contradiction that, actually, do we, okay, actually, we don't need to do it by contradiction. Okay, what can we say about n plus 1? So either n plus 1 is prime. If n plus 1 is prime, we're done. If n plus 1 is not prime, then what can we say? Well, what's the word for a not prime number? It's composite, right? So if n plus 1 is not prime, then we can say n plus 1 is equal to, I don't know, k1 times k2 for some k1, k2 less than or equal to n. Right? So if it's not prime, it's composite. If it's composite, it can be broken up into a product of two things that are smaller than n. But what do we know about things that are smaller than n? Less than or equal to n. Well, what do we assume? We assume that everything less than or equal to n and is can be written as a product of primes, right? So we have k1 and k2 can be written as a product of primes. Therefore, n plus 1 is a product of primes, right? So we're done. Sorry, I was kind of doing that on the fly. I didn't actually write that down in my notes. So anyway, it's fine. But then
K1, K2 can be written as a product of primes. K1 and K2 can be written as products of primes. So their product is a product of primes. Good. So we're done. So we've shown the base case, we've shown that if it's true for all n, or k less than or equal to n, then it's true for n plus 1. So we're done. Okay, so that's theorem 1.7 by induction. So remember when we proved it the first time, we used the well ordering principle. Remember? We used the well ordering principle. So with the well ordering principle, with the well ordering axiom, we said, okay, let's take S to be the set of all integers that can't be written as a product of primes. Therefore, it has the smallest element, right? And then that smallest element, if it's not, if it can't be written as a product of primes, well, it's composite. If it's not prime, it's composite. Therefore, it has two, right? The multiplication of two numbers, but those numbers must be able to be written as a product of primes because the one we chose is the smallest. So anyway, so it's an equivalent proof, but using a different method. Okay, so division algorithm, we really have to kind of write the division algorithm differently to do it by induction. And the for the proof of division algorithm, we're just going to do not the uniqueness part, but just the existence part of the division algorithm. The uniqueness part will be the same, so it doesn't use induction. So let me get a better marker. Okay, and I'm going to run through this kind of quickly. Okay. So to do this by induction, like you were thinking, okay, the division algorithm, we have an A, we have a B, we have an R, we have a Q. What are we inducting on, right? How do we do this by induction? So we're going to, I'm going to have to reformulate the statement of the division algorithm so that we can do it by induction. So here's the statement of the division algorithm. Well, I'll put revised. And here's my revised statement of the division algorithms that I can do induction on. So we start by letting B let B be an element of n. Now this B is arbitrary, so we pick a B first. Then we say for every A in n, A and Z, excuse me, there exist unique integers Q and R such that, and this is our statement that we know, such that A equals B Q plus R and 0 less than or equal to R less than. Okay, so here's our proof. So we're going to do our proof by induction on A. Actually, yeah. So we'll do, first of all, let's assume A is greater than 0, or we'll do cases. Actually, let's do case 1. A is greater than or equal to 0. We're going to do induction on A. Okay, there we go. So if if A is positive or non-negative, we can do induction. Okay, so here's our base case. A equals 0. Okay, so if we had some B and we have some A is 0, we can say that A is equal to B times, what's my Q gonna be? Oh, sorry, 0. 0 equals B times, what's my quotient gonna be? What happens when I divide 0 by B? What's my quotient? 0. And my remainder is 0. Okay. So that works. So this is my quotient. This is my remainder. And I have that 0 is less than or equal to 0 is less than B. So this is my remainder. And I know that it's less than B. B is an element of the natural numbers, so 0 is not included in there, right? And so that remainder 0 is less than any natural number that we picked to begin with. Okay, so our base case holds. Good? Okay. So then let's do induction step. So let's assume that A equals B plus R. Where 0 less than or equal to R less than B. And then we want to consider A plus 1. Well, what's A plus 1 equal to? What's A plus 1 gonna be equal to?
B equals R plus 1.
Yeah. Okay, BQ plus R plus 1. So this is my quotient, this is my possible quotient, and that is my possible remainder, right? So we have some cases. What's one case? Well, if R plus 1 is small enough, we're done, right? So if R plus 1 is well, if 0 is less than or equal to R plus 1 is less than B, then we're done. Right? Then the quotient is Q. And remainder is R plus 1. So the other thing is, what's the other possibility? Well, I know R is strictly less than B. So if R is as big as possible, you know, it would be like B minus 1. So if we add 1 to it, then R plus 1 would equal B. So that's the other case, right? Does that make sense? If R equals B, then we can write A plus 1 is equal to B times Q plus 1. Right? I just absolve that remainder into an additional copy of B. Right? So in other words, let's say, let me do an example. Oh gosh, I was gonna let you out early, it didn't happen. Okay. So let's do an example. Let's say like we have, I don't know, 6 equals 5 times 1 plus 1. Right? Oh, that's not big enough. I want to do 4 or something. Okay, so what's that? So that's 9. Okay. So let's have 9 equals 5 times 1 plus 4. So 9 plus 1 is equal to 5 times 1 plus 4 plus 1. Well, that makes a 5, right? So then 9 plus 1 is equal to 5 times 1 plus 1, right? So I have I'm absolving that remainder into an additional value of the quotient, right? The quotient's gonna go up by 1. Does that make sense? Okay. So so I have that, and so the quotient is Q plus 1. And the remainder is 0, right? So if that's the case, I have that. So so I have done induction on the case for A is greater than or equal to 0. I still have the case where A is less than 0. A is less than 0. And basically what we're going to do, if A is negative, I'm going to take negative A. Negative A is positive. A is negative, negative A is positive.
Is this supposed to be 4 plus 1 or is it 1 plus 1?
Yeah, so right. So it's not, it is supposed to be 1 plus 1. Why? Because this is now a 5, right? And so this quotient, will go up by 1, right? When I absolve that in there. So in other words, I could write it this way, 5 times 1 plus 5, and then I can factor the 5 out. Does that make sense? Yeah. No, it's always good to ask, because I write stuff that's not true on the board all the time. So. It's good to ask. Yeah, Colin?
On the start of the induction stuff, we have R is strictly less than B. So we had the case that R plus 1 is strictly less than B. So is our other case that R plus 1 is equal to B?
Yeah.
That
That's right. Yeah, so if that new remainder, R plus 1, is actually equal to B, then you can pull it out. Yeah. Okay, does that make sense? No wonder you were giving me funny looks. Okay, yeah, so that's what I meant. R plus 1. Okay, so yeah, so that case, we're gonna use the previous case, right? So if we have a negative number, then I can look at the negative of that number would be positive. So I get my Q and R there, and then I have to do a little bit of adjustment because the remainder is gonna not work out quite like we want, but anyhow, we can do that. But let's not do that actually. But I wanted to show you how we can rewrite the division algorithm and use induction with it. So, okay, that's all I had.